All right, let's look at improper integrals. All right, there are basically two kinds of integrals, improper integrals. These are called improper. First kind is it has an infinitely long interval. Second kind is that you might have a finitely long interval, but the function might have an infinite discontinuity. All right, so let's look at an example of each kind. All right, first kind. All right, so if you have an integral over a infinite long interval, right? So like the picture looks like this. So you might start from some finite number. It goes to positive infinity. So you have an infinitely long interval. All right, so let's look at this example. All right, so we have integral from 1 to infinity, 1 over x squared with respect to x. All right, so first thing we need to do is this. All right, since the troublemaker is this guy, if it was a finite number, we know exactly what to do. All right, so we're going to replace that by b. So we tend to use a for the lower limit. Since this is the upper limit, I'm going to use b. So first thing I would do is I'm going to replace infinity by b. All right, everything else stays the same. All right, so if b is a finite number, we know exactly what to do. Right? But these are not exactly the same, so we have to make b value larger and larger. So the good notation in math to do that would be limit as b approaches infinity. Right? So let's evaluate this. All right, so this is going to be equal to, so we're going to take care of the limit later. All right, so here, integrand, so I don't like fractions, so I'm going to actually go ahead and rewrite it as x to the, since it's on the bottom, negative 2 power, right? So I'm going to go ahead and find antiderivative of that would be add 1 to the power. So you have x to the negative 1 and divided by that power, so it's negative 1, right? And then you're going from 1 to b, right? And if you don't like the way this looks, we can rewrite this. This is just the same thing as, so this is the same thing as, maybe I'm going to go down here, negative 1 over x, right? So if you plug in b, so we're going to take care of the limit later. So I'll just put that in there. All right, so plugging b, so it's going to be negative 1 over b. So negative 1 over b minus negative, so it's going to be plus plugging 1. So it's going to be a 1 over 1. All right? But this limit is very easy to evaluate as b approaches infinity. 1 divided by a really big number is going to approach 0. So the first term goes away. What's left is just a 1 over 1, which is going to be 1. All right? So value of this improper integral is 1. Right? So all you have to do is really just to replace infinity by b or a, depending on if it's an upper limit or lower limit. Then go ahead and evaluate it just like we've done before. Then after that, we take the limit as b approaches infinity. All right, so let's look at the second kind. This kind has an infinite discontinuity. So if you look at the picture here, a is fine, you have a finite value, but if you look at the right endpoint at b, you can see that the function has an infinite discontinuity. Right? So let's look at this following example here. All right, so this is going to be, so what's the problem here? So maybe I should draw a picture. If you sketch the picture of this, it's going to look like this. So you have the y-axis here, x-axis here. And problem is this function is not defined at x equals 0. So you're going to have a picture that looks kind of like this, right? So 1, there's no problem at 1. So here's 1. And we're looking at the region. Maybe should use a different color. So this is the region we are looking at. Right? So this is the graph of y equals 1 over square root of x. Right? So in this case, the troublemaker is actually 0. Right? So what you're going to do is I'm going to replace that with, say, a. So this is going to be equal to integral. Right? If a is slightly positive, there's no problem. So we have that. But what we can do is, so a is right here. Maybe I should use this. So here is our slightly positive a value right here. Right? So what we need to do is we can send a toward 0 from the right. So I'm going to take a one-sided limit. So you have a limit a approaches 0 from the right. All right, so that's how we take care of the troublemaker here. All right, now we can just go ahead and evaluate. So you have a limit as a approaches 0 from the right. Right, then we want to find antiderivative. So this is the way this, I don't like the way this is written. I'm going to rewrite it as x to the negative 1/2 power. Right? So if you take the antiderivative, you're going to have add 1 to the power. So you have x to the 1/2 power. Right? Then divide by 1/2 is equivalent to multiply by 2. So I'm going to just put 2 in front. And then it's going from a to 1. Right? So here you have a limit. So you have a limit here. A approaches 0 from the right. And if you want, since that 2 is just a constant multiple, we can place it in front. So I can just put the 2 in front of limit. All right, so square root of 1/2 power is equivalent to square root of x. So this is the same thing as square root of x. So if you plug in 1, square root of 1 is 1, minus plug in x equals a is the square root of a. All right, then as a approaches 0 from the right, you can see that the square root of a is going to approach the square root of 0, which is 0. So we have 2 times 1, so the value is 2. Right? So this is how you deal with the infinite discontinuity case. So if you find an endpoint, or sometimes discontinuity happens in the middle of the interval, then you have to split. But when you find a troublemaker, in this case x equals 0, since function is not defined there, what you can do is you can move slightly to the positive side in this case, then replace that with a, then go ahead and evaluate the definite integral with a in it, then take the limit, just like the infinite interval case. All right, that's it. I hope that this was clear.